and thanks Arturo for inviting us and for amazing tacos and a beer. That always helps before a presentation. Yeah, I'm Jawad Saleemi. I work for Ruter, and there I lead a team of machine learning and data scientists. So we have a few use cases that we're using machine learning and AI to improve our services and to provide a better offer to our users, which are including you guys. But before we get there, the presentation is divided into 3 parts. So a little bit about Ruter, what we are. I'm sure you all know about Ruter, but just a little bit more context into what kind of data do we have and how old we are, for example. And then the next part would be the AI use cases, where we have used AI and machine learning for what use cases and how it has helped, or it hasn't helped. And then in the end, we'll have a few slides about MLOps, how do we manage the operation part of the machine learning. So Ruter, a public transportation company, as Arturo said, in Oslo and Viken. We are partially owned by Oslo Commune and partially by Viken. Established in 2008, we operate around 4,800 physical stops, and we operate around 19,000 trips per day. And for those 19,000 trips, we have around 500,000 departures every day. And we move around 1 million people per day from point A to point B. And that's pre-corona stats. Of course, things look a bit different in the last 2 years. But our latest data shows that we are around 92-93% of what we had before corona. So we have people back, which we're really, really happy about. And we cover around 300,000 kilometers per day. So that includes driving and sailing. To give you an idea about the data that we have in Ruter, we have both streaming data and batch data. For streaming data, most of the data comes from our vehicles. We have a lot of sensors on board. We have sensors telling us how many people are getting on and getting off the buses or trams. What is the temperature inside and outside? What is the weight of the bus? Of course, the position of the bus, how much distance the bus has traveled. So that's, of course, one of the new buses. Not all buses are equipped with the same kind of or same number of sensors. And we even have, in some cases, the data about how fast the wind wipers are moving. So combine that with weather, we are kind of, mini weather stations moving around in Oslo. So now that we have a little bit more understanding of Ruter, let's talk about the AI use cases we have, in Ruter. So the first, the machine learning team in AI is around 2 years old. So we started in 2020. That's when we had our first use case. And that was to help our customer service team with machine learning, with offloading them or helping them in some way, so that they can, they spend less time on those mechanical kind of complaints that they get all the time, but more time on more complex complaints. So what happened is that we get a lot of complaints and inquiries, and a big chunk of those complaints are about, bus being late, or the bus leaving early, or bus being cancelled. That's not a surprise. But if you look at the text of those complaints, so basically the way people send us complaint is that they go to Ruter Contact NO, the web page, and then there's a text field, and they write it there, and they fill up some metadata. And if you read the text of those complaints, where it's always like bus late or insult or left too early, it's the same text. It's, I'm standing at bus and I missed the bus again, and Ruter sucks or something like this. So we thought we could use machine learning to automate this process, to automatically detect these mechanical complaints, which always have the same text and always have similar kind of reply, so that our customer complaint people can actually focus on better and more, or not better, but more complex use cases. So we made an AI agent which sits in parallel to the case handler, and it automatically categorizes the complaint based on the historical text data that it has been trained on, and then it automatically replies to the person who sent the complaint. So before this case handler, a customer could experience like a week of delay between they send us a complaint and they got a reply back, especially in summer times. But with this, since it all happens automatically for simple use cases, the response time is around 20 seconds. So that's a big win, not only in terms of customer satisfaction, but also in terms of our customer support team having more time to look at better things. We also did, since it's all text, so we did some sentiment analysis, and we geographically plotted it. I'll show you the dashboard in a while. So it's just snippet from that dashboard. So here you could see the sentiment of the complaint all the way from green to red, and green, yellow, orange, and red. And so that the customer handlers could focus on those geographical areas where most is red, and then see what's going on. We did some unsupervised learning as well to see what kind of new categories we could find. So if you go to our contact form, there's already a list of categories, and you can choose, like, if it's traffic deviation, or if it's about if you lost something on the bus or something. But we thought, since we have all the context data, all the text data, what if we run unsupervised learning and see what else are people talking about? So we found out that a lot of people were talking about accessibility issues, like, if you're using a wheelchair, or if you have a bonnet or a baby stroller. There were cases where people are complaining about accessibility issues. Then there are a lot of people who were not happy about, the buses closing the doors, or, you're just at a stop and the driver closes the door, and then you, of course, get like really angry, and then you send us a complaint. Another thing which we found out was people complaining about music. And there were like two main categories. There were one group of people within that music that they complained that the music was too loud. And that makes sense. Of course, you want to have a nice experience. But there was another group that complained that they did not like the driver's taste in music. So that, I don't think we could do anything about that. We also use a combination of machine learning and a lot of kind of hard-coded, business kind of rules, and a lot of whitelist and blacklist to anonymize the data. So what happens is that when people write to us, even though it's a free text, and we tell them, please do not give us any personal information. But let's say if you are going to hospital and you miss the departure, so you might end up writing that, I missed the departure, the appointment with my doctor. Or if you are asking for a refund, you might send us in this text field your bank account number. And these are all personal information that we don't want to have. But because of this, we could not share this with other people in the inside Ruter as well, because of GDPR issues. So what we did was that we used machine learning with a combination of a lot of other things to remove this personal information. So if you see here on the left side, so the email address is replaced, and telephone number is replaced, and number is replaced. Which made it so that we could share this data internally with a lot of different teams. So they can look at not just the statistics, but also actually the context of the complaint, what the person actually talked about, to get a better idea of what's happening on ground. And then we combine all that into a dashboard, which we call Customer Insight Dashboard. And there you can see like different kind of categories that people are complaining about, the trend in the different categories, the geographical areas which are more dense. And on the left side, you can see the text. And this text is like the cleaned version of the text. So you could start all the way from statistics, but you can drill down all the way to one particular complaint and see what the person was talking about without knowing who the person was, without having any personal information on that. Here's an example of sentiment analysis. So this is the route for our bus number 100. And you see those green and red spots. So the green ones are, people are complaining, but they're like, okay, they're not super pissed. But the red ones are where like people are, quite angry. And you see like on Alnabru or Vålerenga, maybe there's something that we should look a bit more deeper into. And you can, we have like the filters for time and everything. So you could do per day, or you could do, per specific time. Another project which we're working on is capacity prediction, where we try to predict much in advance how many people would be at the departure or in the bus when you take the bus. So this feature is already out. There's a snippet of our nice app. On iOS, you have the 100% of people who have this feature enabled. On Android, we are rolling out gradually. So the next time you search for a journey with our app, please check it out and see if it was correct. There's a possibility to give us feedback and tell us if the predictions were correct or not. We have the results so far. We released it last week, so it's been around 10 days. Around 83% or 42.5% of the people, and this is based on around 1,000 users. 42.5% of the people said that the prediction was correct, precisely correct. 41% said that it was off by one category. So we said like many places available, but it was actually few places available. So it's still an okay prediction. But 17% of the people said that the prediction was not correct. We said many seats available, but when they actually took the bus, it was full. And these are the kind of cases where we actually have to work a bit more and see what we can do in our models to make it better. But it's an iterative process, so yeah. Let's see if we manage to make it even better. We're also using machine learning to predict the busyness of stops. So how many people are going to get off or get on, let's say tomorrow on bus 30 at Jernbanetorget at 12 o'clock, so per departure. And we feed this information. So this is a snippet of our display from within the buses. And here you see like the next 3 stops from the position where you are. But on the right, you see the next 3 most relevant stops. And they don't have to be the next 3 in line, but they are the next 3 where people are most likely to go out. And this varies depending on the departure. So it means if it's a working day at 8 in the morning where everybody's going to work, those departures might, those stops might be different than if it's a weekend at 4 in the afternoon. So it's a bit more contextualized information for the passengers who are using the buses. If you have used our app, you might have noticed that every time you use the app, you have to search for a destination where you want to go. We are working on a feature, and this is still a work in progress, where we are going to use machine learning to, based on your historical patterns, where you have normally been going, right? Most of the people have kind of a static pattern. You know, it's a weekday at 8 in the morning, you go to work. At 4 or 5, you come back. It's a weekend, maybe you go to training center, maybe you go to play some sports or whatever. So based on historical pattern, we want to be able to guess where you want to go next. So when you open the app, the suggestions are already there where you want to go. And that's a product that we're currently working on. We have an on-device model, which is already operational, and we are testing it with a test group. But we also are working with Datatilsynet in their Sandkassa project, where we're going to, for those of our users who give us access to, or who give us consent to gather their data, we're going to then use like a traditional machine learning on a central model to provide better personalized journey recommendations the next time they use the app. So it's a work in progress. We'll share more results when it actually happens. Ticket inspection, we're using machine learning there as well to optimize the inspection routes. So because Ruter spend a lot of money on doing controls, and we want the controls to happen where they're actually effective.
It's good for me. Can you share more details on this?
Maybe after a few beers. And then we're using, Ruter also has an on-demand service called Concentra, where, for our users who are older than 65 years, they can call and we can pick them up from using these pink buses from A to B and then back to A. And they don't have, today they don't have a smart way of allocating these buses. So we're going to use machine learning we are using machine learning to predict the region where the demand is going to come from. So then we can better allocate these buses when they're, out in the operation. So what happened today is that when nobody's calling them and when they have an idle time, they just wait and they park somewhere and they wait. But if we could predict where the next call is going to come from, then they can actually drive there already in that area. And then when somebody calls, it's a faster response time. It's, the buses around the corner, so they can just go there and pick them up. So better customer service as well. So that's one of the use cases. Off to MLOps. This is a picture, very famous picture from Google. Everybody knows it. But if you look at this picture, the actual model development part is this little black box in the picture, right? But to deliver that data, or to be able to make those predictions or that data product, and to deliver it to the customers or consumers who actually can use, it's a lot of work involved. It's a lot of data engineering. It's a lot of data validation. It's a lot of monitoring, a lot of management, and then to serve the data in a format that the customers or your consumers actually can use. It's a lot of work as well. So I guess that's why we need MLOps. Here is a very high-level architecture of how things look at Ruter. We have domain teams, which produce data like APC data coming from sensors, or data about or the position of the bus, or when the bus was where. And they produce all this data in Kafka. And then there are business teams sitting on the other end, which needs this data from Kafka in a bit more structured service level data, which is business intelligible. And then data science, which machine learning team is a part of, they sit in between, and that's what they do. They get the data, which is raw data from Kafka, and then they process it to be able to be used for business intelligence or analytics, but also for machine learning. But then we feed the data back to Kafka through machine learning, these predictions, for example. So the capacity predictions, then we feed it back to Kafka, then it can be picked up by our app team. So we need kind of a structure or an architecture to support all that to work seamlessly. But when we started at Ruter, we didn't have any of our infrastructure which supported machine learning or MLOps. So we were doing actually like this. We had one person on his local machine downloading the data, and then doing all the magic, and then uploading a model.csv file on a GitLab, and then somebody else could download it. But of course, that's not sustainable. That's not reproducible. That's not monitorable. We don't know what is going on inside. But we spent quite a bit of time, and after many kind of iterations and going back to drawing boards, and in correlation with the evaluation of our products as well, our typical machine learning pipeline looks something like this. This is all based in AWS. We heavily use AWS in Ruter, and all our services are from AWS. We use SageMaker. If you use AWS, you might know it's a management service for machine learning jobs. It supports everything from data ingestion to data wrangling to all the way to model deployment and inference and A/B testing and all that. So we use that for our pipeline orchestration as well. It provides somehow similar feature as MLflows. You can do experimentation, tracking, and all the fancy things. And then each step here is a containerized application, where we use GitLab CI/CD to do version control. And each of them, they produce logs using a Amazon CloudWatch feature, which is a logging framework for Amazon. And then based on those logs and alerts, we create dashboards where we can monitor the pipeline health. But also, it creates alerts which are integrated directly to our Slack channels. So if one of our pipeline fails, let's say data validation failed, then we would get an alert right away on our Slack channel. So before our downstream users know anything about the state of the pipeline, we would know. We would be the first one to know. And then we can go there and see what's going on, and we can probably re-trigger the pipeline after fixing the problem, or we can at least tell our downstream users that they can expect an issue. And all that is in Terraform, and all that is in GitLab CI/CD. So when a new person starts working, or a new developer wants to create a new feature in a model, we have designed our pipelines such that when you create a new branch, it creates a new developer's infrastructure, which is sandbox from everybody else, and you get all the resources by default. So you would get a kind of replication of this pipeline in a development environment without affecting any of the other things. And then the person can work on it and then try different things. And when he or she is confident about that everything is working fine, so you can merge it back. And and when you merge it back, then it can destroy all the dev infrastructure. So it can do a nice cleanup. And that makes it possible that multiple people can work on the same product at the same time without affecting anyone else. If you look a bit deeper into SageMaker's IDE, it looks a bit like this. So on the left side, you can see all the runs for the pipeline. So you see we run it every day. And if you go a bit deeper, we have like different steps. And each step is a containerized application with GitLab CI/CD and version control and all that. And you can click on it, and then you can look at the logs. You can look at the input parameters, output parameters. You can see like which S3, which is the storage, AWS storage, which one is using, and if there were any errors or warnings or whatever. So it's like one place to just go and have a good understanding of what's going on. But so far so good. We have the pipelines in control, and we have data validation, and we have if something fails, we would know. But how do we know that when we deploy the model that it's working, right? It's doing the job that it's supposed to do. It's making the predictions with the quality that we expect it to produce. So we have some dashboards for that purpose. Here we use AWS QuickSight, which is a BI and analytics tool by AWS. Fits very well with Terraform and infrastructure as code and all that. And there, it automatically every day picks up the new prediction that we have made, but also when the actual data arrive from the APC sensors on the buses, then it picks the data in as well. And then we can compare, or it makes this visualization so that we can compare how off we were on each and every departure. So you can go, in the dashboard, and you can say tomorrow at 12, Jernbanetorget, line 30, direction Fornebu, how off we were, how off our predictions were. So you can start from all the way from high level and go all the way to each and individual departure. This is another dashboard for demand predictions, which are, I just mentioned. And here on the right side, you have what we predicted. And on the left side, you have true demand. And if you compare, there's a little difference there, but it more or less looks quite nice. Of course, it's, it's for a specific time window that I have selected there. Results don't always look as good. But at least it gives us an opportunity and possibility to go there and see how well the models are doing. It's possible to add triggers as well. So if your average residual on one day is above a certain threshold, so then you can get an email or something, and then you can go back and see what is going on. The way we work at Ruter, or in the machine learning team at Ruter, is that we have end-to-end responsibility of our machine learning products, all the way from data ingestion to data delivery, which is predictions or insight or whatever. So we don't have any dependency besides the source data. We do our infrastructure ourselves, we do our pipelines ourselves, we do our monitoring ourselves. So the same person who is working on a product or on a project developing a model is the same person that actually monitors the model in that or productionizes the model as well. So it's like a complete end-to-end life cycle. He is responsible for that. But it works for now because we don't have so many use cases. But in case, let's say we have 50 different products, we might want to think about having a separate machine learning platform team, which then provides the services to developers. But so far, it's working really well for us. Our tech stack looks a bit like this. We very heavily use Amazon Web Services. We use Terraform for everything, so all the infrastructure is in Terraform, which means that if something accidentally happens, we can just by one click bring up the whole infrastructure. Of course, we'll lose data, but at least our infrastructure would be up in a heartbeat. We use Kafka for data sharing, so all the prediction that we make, we dump it on Kafka. And the good thing about that is that we have schema enforcement there, so we get data contracts. So the producers and the consumers know exactly, or the consumers would know exactly what data to expect. And yeah, the usual thing, we have Docker and a lot of Python, and we use SageMaker for management services. There's a Medium article as well if you want to read a bit more in detail about how these things work together, especially SageMaker and GitLab and Terraform. Please go there and read it and let us know if it was useful. Yeah, that's all what I wanted to share with you. Hope it was helpful.